What is the nature of the universe? This question is undoubtedly one of the deepest and most captivating ever posed by humanity. For countless centuries, people remained ignorant of the grand cosmic processes unfolding across the vast expanses of space. To make sense of the world around them, they crafted myths and legends, stories that either offered explanations for observable phenomena or provided comfort in the face of the incomprehensible. However, with the advent of science, the horizons of understanding expanded dramatically. Scientific methods enabled hypotheses to be tested, lending an unprecedented degree of confidence to the pursuit of knowledge. As our conceptions evolved, a new field emerged: cosmology, the science dedicated to studying the universe itself. Now, after centuries of speculation and poetic tales, we are beginning to grasp some of the most profound ideas ever conceived by the human mind. What, then, is the nature of the universe? Let us explore this together. By the early 20th century, the scientific community already recognized that Earth was immensely ancient. Charles Darwin's theory of evolution strongly suggested our planet was at least several million years old. Lord Kelvin, a preeminent engineer and physicist of his time, corroborated Earth's antiquity through calculations of its cooling from an initially molten state, a process he estimated required no less than 1 million years. Yet Earth's precise age remained unknown, and logically, the universe itself had to be at least as old, if not older. The prevailing cosmological model of that era depicted the universe as static and unchanging, essentially as it appears to us today. It was widely assumed that, on the largest scales, the cosmos remained in a state of equilibrium. Stars might be born and die, but the universe as a whole was thought to be eternal. It had always existed, would always exist, and had always contained galaxies. Although some dissenting views existed, this was the dominant perspective among astronomers of the time. This mindset carries profound significance when interpreting astronomical observations, as preconceived notions shape the framework through which we understand new data. When observations defy these frameworks, a dilemma arises. Either the data is flawed or misinterpreted, or the framework itself is wrong. Challenging foundational assumptions is a monumental step, demanding rigorous scrutiny and healthy skepticism. Science resembles an intricate tapestry. Pulling a single thread may require rewoven the entire pattern. Occasionally, though rarely, that thread must be pulled. The first such thread emerged in 1912. That year, astronomer Vesto Slipher, perhaps the most memorably named figure in astronomy, began photographing the spectra of so-called spiral nebulae to determine their properties. It is crucial to remember that, at the time, the true nature of galaxies was still unknown. Over 7 years, by 1917, Slipher had studied 25 such objects and reached a startling conclusion: nearly all exhibited strong redshifts. In other words, the vast majority appeared to be receding from us at astonishing speeds, millions of kilometers per hour. What could this possibly mean? Two independent lines of inquiry began converging. One belonged to physicist Georges Lemaître, who in the 1920s deeply studied Albert Einstein's work, particularly the equations describing the universe as a whole. Einstein had concluded the universe was static and stable, but Lemaître disagreed. He realized that an expanding or contracting universe fit the equations far better, and, given Slipher's redshift observations, he proposed that space itself was stretching, causing galaxies to appear to move away from us. Around the same time, another insightful physicist, Alexander Friedmann, reached a similar conclusion. Meanwhile, astronomers were striving to measure distances to these nebulae, now known to be independent galaxies. As mentioned in the earlier episode on galaxies, Edwin Hubble and his assistant Milton Humason led these efforts. By identifying specific stars in the Andromeda galaxy, they accurately determined its distance. They then examined the same galaxies Slipher had studied and measured their distances as well. Comparing these distances with Slipher's redshifts, they uncovered a remarkable pattern: the farther away a galaxy was, the faster it appeared to recede from us. This bears repeating, for it is profoundly important. The more distant the galaxy, the greater its apparent speed of recession. Other astronomers reached similar results, but Hubble and Humason's work decisively settled the matter. We now know this holds true for every distant galaxy we observe. All exhibit redshifts, and all are moving away from us. This directly supports Lemaître's insight: the universe is expanding. But what does it mean for the universe to expand? How is this even possible? Several approaches help conceptualize this phenomenon. Lemaître himself suggested imagining cosmic time running backward. If galaxies are moving apart now, then in the past they must have been closer together. Rewinding time far enough, all matter and energy in the universe would converge into an extremely dense point. This is a startling idea, envisioning every star, galaxy, atom, electron, and proton compressed into a single, unimaginably dense mass. Yet that is precisely what observations imply. Lemaître called this the primeval atom, or, more poetically, the cosmic egg, a fitting metaphor. But it carries deeper implications. Compressing all the universe's energy into one location would make it unimaginably hot. In its earliest moment, the universe was an intensely hot, dense point. Then, for reasons still not fully understood, it underwent a sudden, violent expansion and began to cool. This resembles an explosion occurring everywhere at once, and what better name could we give it than the Big Bang? The term Big Bang entered popular usage thanks to astronomer Fred Hoyle. He first used it in a radio broadcast and later in print, but ironically, he meant it dismissively, as he was skeptical of the theory's validity. To his chagrin, and that of many fellow astronomers, the name stuck. Yet many now find it apt. Though not perfectly precise, it is vivid and evocative. At the time, this concept seemed radical, clashing with all established cosmological views. In science, however, any theory must offer testable predictions before it gains serious acceptance. What observable predictions does the Big Bang model make? We know light travels at an immense, but finite speed, 300,000 kilometers per second, or roughly 1 billion kilometers per hour. Thus, we see celestial objects not as they are now, but as they were when their light was emitted. Sunlight takes about 8 minutes to reach us. We see the Sun as it was 8 minutes ago. The nearest star system, Alpha Centauri, is 4.3 light-years away. We observe it as it was 4.3 years ago. The Andromeda Galaxy lies 2.5 million light-years distant. Its light left when early hominins walked the Earth. The farther we look, the deeper into the past we peer, a principle known as look-back time, a vital tool in cosmology. One might assume we could observe the universe all the way back to the Big Bang itself. But a barrier exists. At a certain point in the past, the universe was so hot and dense it resembled the surface of a star, luminous but opaque. As it expanded and cooled, it gradually became transparent. The earliest moment we can observe is precisely when this transition occurred. What does that moment look like? Using physics and calculations modeling matter, energy, space, and time, astronomers predict this surface of last scattering occurred a few 100,000 years after the Big Bang. Based on look-back time, they can calculate its distance and expected redshift. Remember, redshift stretches light's wavelength. The light emitted then would have been visible, like starlight, but after billions of years of cosmic expansion, its wavelength would have stretched into the microwave part of the spectrum. In 1965, 2 radio astronomers announced the detection of a faint, uniform signal in their telescope, a background hiss coming from all directions in the sky. They exhaustively ruled out all possible sources, even cleaning pigeon droppings from the instrument. The only plausible explanation was that this was ancient light, its wavelength stretched by cosmic expansion. They had discovered the afterglow of the universe's fiery birth. the cosmic microwave background, CMB. In the 1990s, satellite observations dramatically refined CMB measurements, confirming it as an established fact. This radiation had been predicted by the Big Bang model, and now we observe it in exquisite detail. This discovery marked a giant leap forward in cosmology. But the redshift of distant galaxies and the CMB are not the only evidence supporting the Big Bang. The model also accurately predicts the abundance of light elements. In the hot, dense early universe, only subatomic particles existed. As it cooled slightly, these particles fused into heavier nuclei. The Big Bang model predicts specific ratios of hydrogen, helium, and trace elements, and these match precisely what we observe throughout the cosmos. Moreover, the sizes and distributions of the largest cosmic structures, galaxy clusters, and cosmic voids, align with Big Bang predictions. Numerous other lines of evidence converge on the same conclusion. Today, virtually all astronomers accept the Big Bang as the correct description of the universe's origin. But what does this mean physically? A common misconception is that the Big Bang was an explosion in space, with matter flying outward from a central point. This is incorrect. Space itself is not a passive container. It is a dynamic entity that can be warped by mass and energy, what we experience as gravity. When we say the universe is expanding, we mean space itself is stretching, carrying galaxies along with it. Imagine a rubber ruler with marks drawn on it. As you stretch the ruler, the distance between marks increases. If the ruler doubles in length, marks originally 1 mm apart become 2 mm apart, while those 10 cm apart become 20 cm apart. The farther apart two marks are, the faster they appear to recede from each other. This is exactly what galaxy redshifts reveal. Crucially, galaxies aren't moving through space. They are nearly stationary, while the space between them expands. This isn't mere semantics, it's a physical reality. From any point in the universe, observers would see all other galaxies receding, just as every mark on the stretching ruler sees the others moving away. Einstein's equations implied this, and Lemaître grasped it intuitively. The Big Bang was not an explosion into pre-existing space. It was the beginning of space itself expanding. The universe isn't expanding into anything. There is no outside. It is all there is. Consequently, the universe has no center. Picture our ruler bent into a circle whose diameter grows over time. No point on that circle is the true center, yet from any point, all others appear to move away. Similarly, every location in the universe appears to be the center of expansion, which means none truly is. No place is more special than any other, all are equivalent. Admittedly, grasping these concepts is challenging, even for experts. Yet they form the foundation of our modern understanding of the cosmos, revealing a universe that is dynamic, evolving, and profoundly interconnected. Yet mathematical calculations, combined with all observations made in the distant universe, provide compelling confirmation of these ideas. Amid all this dizzying strangeness, one central thought must not be forgotten: the universe had a beginning. And the evidence for this is tangible. Moreover, by measuring the rate at which the universe is expanding, scientists can use sophisticated calculations to travel backward in time and determine its age. To date, the most precise estimate places the age of the universe at 13.82 billion years. Or perhaps it's better to exclaim, 13.82 billion years. This is a truly staggering figure, representing a time span nearly 3 times longer than the age of the Earth. Yet the most astonishing thing is that such a calculation is even possible. The human mind has proven capable of discoveries on this grand scale. Our modern scientific investigations have led to a remarkable finding concerning distant galaxies. Their spectra exhibit a distinctive redshift, a definitive sign that they are moving away from us. This phenomenon, in turn, points to the ongoing expansion of the universe. The logical conclusion of such a large-scale process is that, at the very beginning of its existence, the universe was in an extremely hot, dense state before rapidly expanding and gradually cooling. This foundational model of the universe's early behavior is known as the Big Bang. The Big Bang hypothesis received strong confirmation with the discovery in the 1960s of cosmic microwave background radiation, sometimes poetically called the surface of last scattering, or the echo of the fireball. This background radiation is a remnant from those primordial times when the universe was far more compact and hotter. In addition to this key piece of evidence, numerous other scientific observations further corroborate the theory's validity. Drawing on this extensive and rigorously verified body of data, scientists have been able to perform precise calculations that yield a reliable estimate of the universe's age. According to these findings, our universe is an awe-inspiring 14 billion years old.